Hey, physical science, it's Tuesday, April 14th. We're going to cover pages 469 to 472. Let's get right in it. We're talking about physical properties and physical changes. Now, if I take this Mickey Mouse balloon here, and if I stretch it, is it still a Mickey Mouse balloon? Yeah, and it'll snap right back, okay? That's a physical property that it'll snap right back. But it also is a physical change when I do this. It isn't the same look, but it is the same item. You have not changed the identity, so we call that a physical change, not a chemical change. All right, so what are some other physical properties? The color is yellow, but could I change the color? Sure. I'll take this marker and I'll put a mark across it. It's blue. No, it's yellow. And it's still a Mickey Mouse balloon. So you have not changed the identity of the substance, the material. You just simply changed its color. Now, sometimes color change is evidence of a chemical change, not a physical change. And that would be in the case of rust, you know, that kind of thing, mold. When something in your refrigerator is rotten, you know, like cheese, changes color. That's a chemical change, but in this case, changing color is just painting it or coloring it with a crayon. It's still a Mickey Mouse balloon. You have not changed the identity. If you change the shape of something or the size or the density, oh, okay, now you can't change density. The density of this particular item here called a what? Paperclip? Well, let's see, it's based upon the fact that this is made out of iron and it's coated, I think, with zinc to keep it from corroding. Kind of like a galvanized pipe, if you please. Anyway, so that density of that iron and zinc will not change. Density is a physical property, but it doesn't change. Whereas shape is a physical property, but it does change. But it's still a physical property because when you do change the shape, you do not change it to a different item. Melting point is a physical property, the temperature at which something melts. Ice always melts at 0. And it doesn't change to a new substance. When ice melts, it goes from H2O to H2O. Isn't that nice? So boiling point is also a physical property because the temperature at which it boils at a certain pressure is always the same. For water, if it's 1 atmosphere of pressure, we've already talked about this, then it will boil at 100 degrees Celsius. But if you're in the mountains like we are, it might boil at 98. And you can't get it any higher until all of it is boiled off. And then once it's all turned into a vapor, then you can continue to add heat and it will go up in temperature. But during the change of state, it does not change its temperature. The boiling point is fixed for a particular pressure. And so you can say that changes of state are always physical changes. Changes of state, when something melts, when something boils, when something condenses, when something freezes, when something sublimes, when something resublimes or deposits, it's always a physical change because when the ice melts, it turns from H2O ice to H2O liquid, water. And then when it boils, it turns from H2O water to H2O vapor. And so it's still H2O. So you do not change the identity of a substance when you change it by physical change. Let's say that this piece of string is this long. Now let's change the length of that string. All right, I'm going to change the length, make it shorter. Is that still string? Yep. So it was a physical change in the string, not a chemical change. The mass, the volume, the density, the temperature, all of those are physical properties. I'm on page 470. Now, a magnet. When you take a magnet and hook it next to a paper clip, look what happens. And the reason is because, remember we talked about magnetic domains? They align, and this becomes like a little magnet attached to a magnet. And that's magnetite, you know, that lodestone and all that. Okay, and so that magnetic property can be used in separating mixtures. Now, there is a property on page 470 at the top called ductility. And there's another one called malleability. So we'll say ductile and malleable. Metals are ductile and malleable. Ductile means metals can be pulled into wires like this through a die. A die has a little hole in a big old metal piece like this. If there were a hole drilled all the way through, you could take a piece of metal that was a thicker wire and you could poke it into that hole, and you could somehow pull it through that hole, and it would stretch on its length, kind of like pulling taffy, and it would become a smaller wire. That's called ductile. Metals are ductile. They can be pulled through a wire, extruded through a wire, through a die, and they can be turned into a wire. Now let's take this wire and show you malleability. Malleable sounds like a mallet. And so I'm going to go ahead and hit this with a mallet, a little hatchet here. Not only do metals get pulled through a wire and become through a hole and become a wire, you can also take a metal and wham on it, and it will spread sideways like a sheet. If you take a look right there, you will see that it has smashed from a wire into a flat sheet. And that's why you can make metals become sheets like this aluminum foil right here, like that. In fact, you could whack on that sheet and make it a thinner sheet, and it would spread. And it has to do with the bonding of metal atoms that we'll talk about in chemistry. All right. Using physical properties to separate mixtures. I think in the first section, I told you that we could separate mixtures by using physical processes. So I'm going to make a mixture here. I'm going to use this thing. I've got this mixture is dominoes, paper clips, salt, and mud or dirt. Let's let you see it as I pour it in. See, dirt. Now the question is, how can we separate that out physically without turning the substances into different materials as we do it? Well, here's a good way. Just pull the domino out. Did it turn into a petunia when I pulled it out of there? No, it's still a domino. So I can separate mixtures by physical means. How are we going to get the paper clips out of there? I got an idea. How about if we just take a magnet to it? Look at that. Here come both of those paper clips right out of there because of the property, the physical property called magnetism. Now, we've got nothing left except for mud and salt. So what are we going to do to get the mud out of there and the salt out of there? Well, first of all, we're going to add some water. That's the trick. When you add the water, what dissolves? The salt does. The salt does. And so you can take it through a filter, which may look more like this if you look at it through a microscope. Looks like a mesh. And this water with that salt in it just goes right through this like as though it were going through the mesh. And guess what gets caught on the inside of the filter? It's that mud. So what'll drip through a filtration process is the salt water. Now, when you have salt water, how are you going to separate it by physical means? Well, you're simply going to heat it up. You're going to heat it up to the boiling point of water, because the boiling point of mud is a lot higher than the boiling point of water. So the water will boil off and the mud will remain behind. And all I will have on the bottom of this beaker is just the mud. No. I strained out the mud with the filter, and then I had salt water. So all I would have left behind in here would be the salt. The water will boil off because you're separating them by differences in boiling point. All right, so look on page 471. When you do these things that I just talked about, physical changes, freezing, boiling, evaporating, condensing, that's changes in state. Those are physical changes. And change in size, the shape, state of matter, that's a physical change. The color, change the color, change. When iron is heated, it glows red. Then if it's heated up to a higher temperature, it glows white, but it's still iron. So it's a physical change by heating it up. Using physical changes. On page 471 at the bottom, we talk about making water that is drinkable. We call it potable. Some people call it potable water. That's something you could do if you wanted to be kind to people in third world countries that don't have fresh water. You could theoretically go over there and help them dig a well. And then you could use some photovoltaic panels maybe and use it to drive a pump and pump the water up out of the ground. Any person that would know that you're going to go do a mission trip like that, project like that, would donate to that if they're if they care about others, like I believe Christians should. Page 472, distillation. 472. This is kind of the process that's used up there off of the Nolichucky River, back in by Clark's Creek in that area. I know because I used to run my cross-country team back there. And so what happens is they get a 55-gallon drum, and they get their slurry, their mush, and they heat it over the fire. And it's rotten. And so there's like alcohol. And to separate the alcohol from all of the mush, what they do is they heat it up. And the first thing that comes off is the alcohol because it has the lowest boiling point. And the rest of it, the water and the corn fibers and all that other stuff, they stay behind. And it goes ahead and the vapor, the alcohol vapor goes down a pipe. As you can see, it's called a condenser. And in that condenser, it cools and it becomes droplets and it drips into a bucket. That's called distillation. That's the process by which they separate crude oil. They separate it by boiling points. And so some things boil off more quickly. And I've already talked to you about this. The natural gases come off first, then the jet fuels, and then maybe the gasoline, the diesel fuels. And the highest boiling points, the ones that come off last, would be the candle wax, paraffin, and like the asphalt and that kind of thing. And all of those are parts of crude oil, and they separate it based upon boiling point. And that's a physical change. It's not a chemical change. They're just pulling apart a mixture. See ya.